My name is Jan Dutton, and I am the CEO of Prescient Weather. And today I'm going to talk about long-range forecasting, and in particular around capacity building. So those that came, thank you very much. I appreciate it. And I'm going to start by sticking my neck out a little bit because we just had a fantastic conversation about capacity building. And the reason I and other private companies are here because we think we can help you with the technology component of the capacity building. Many of the elements, and we will talk about them here, we're probably going to be essentially unable to help you with, but the technology component, it's why we're here. So to start off, we're going to look at a subseasonal forecast. So unfortunately, in very early March, there was severe flooding in Ecuador. And what we've got is this is the observed situation that occurred from the 27th of February to the 5th of March. The key here is percent of normal precipitation. And we see right here on the coast of Ecuador, precipitation was off the charts. So it was probably 1,000% of normal where it actually happened. And there was significant flooding. You can search Google News and you'll see the flooding events. And what we have here is a 4-week lead forecast, a 3-week lead forecast, the 2-week lead, and the 1-week lead forecast. And these are from the ECMWF Extended Ensemble forecast. And the key is that these are in probability format. So notice this down here is not the precipitation. It's a probability in terms of the probability of below normal, normal, or above normal precipitation occurring. And so if we zoom in, there's a little splotch of green here. And what this shows is an increased probability of above normal precipitation. And then we go to week 3 and we see the probabilities are a little bit stronger. Week 2, stronger again. And then by 1 week in advance, the probabilities in this, so here's a 90 to 100% probability of above normal precipitation. And then the event actually occurs on this particular week. So within a properly calibrated subseasonal forecast, this is not unusual. Now, I can't say for every precipitation event, record-breaking precipitation event, there's a signal 4 weeks in advance. But what I've seen, whether it's a heat wave, precipitation event, or even dry conditions, you see this evolution of probabilities that can lead to a severe and disruptive event. Now, I also want to highlight there's also severe and disruptive events, like the models don't pick up 7 days in advance either, which is why this is one element of an early warning system in terms of monitoring for the probabilities of severe and disruptive events. And so a lot of the presentations and a lot of the discussion around early warning systems focus somewhere in here, in either observing conditions and warning on them, or a weather forecast, 5 days, 10 days. And to be clear, I'm focused on subseasonal forecasting, so weeks in advance, and then seasonal forecasting. So that would be months in advance in this case. And the difference between a weather forecast and a subseasonal or seasonal forecast, the weather forecast predictability is generally driven by the initial conditions. So sensing what's happening right now and then running your model. And then the longer scale predictions are based on boundary conditions. So the sea surface temperatures, soil moisture conditions, and really, I'll say like inter-atmosphere dynamics as well. So in terms of capacity building, right, there's 5 key areas for capacity building. We actually talked about, I think, all of them this morning, one way or another. And as I mentioned, as a provider of a service that provides long-range forecasting, like I can't help you with institutional and organizational capacity, but I can help you with infrastructure and technical capacity. So the product, the World Climate Service, it's been in development since 2009. And it's just been a slow incremental improvement of the information that becomes available. And we're then also talking a little bit about human capacity development. So when I stood up, I mentioned, I asked people about Python, and they say they know it, but I learned they actually don't. And so leveraging available technologies helps bypass a human capacity, where in the end, the point is to create a forecast. But to get from data to creating a forecast requires an awful lot of technical and human capacity. And the point is that we have that capacity within the company, and we're able to enable forecasts to allow for early warning systems weeks or months in advance. So just a highlight, a modern seasonal to subseasonal forecasting system is processing hundreds of data per year. And so in the medium range, there's models like NOAA's Global Ensemble Forecast System. There's the ECMWF Ensemble. The ECMWF last year released the AIFS, the Artificial Intelligence Forecast System. And then in the subseasonal range, the key model is the ECMWF Extended Range model. So that's a forecast of 46 days. It's 101 ensemble members. And it is, there's a lot of data associated with that model, which I'll talk about a little bit more. But there's other subseasonal models, like the Climate Forecast System, the Global Ensemble Forecast System, and the Japan Meteorological Agency. And then there's even more available for the seasonal models. So the Canadian model is very popular, CANSIPS, because everything is released on the 1st of every month. Again, the ECMWF is popular. It's released on the 5th. And then the Copernicus program in Europe releases now 8 models. They just added the Bureau of Meteorology seasonal forecast model. And that data is all released on the 10th. So these models are updating in real time, updating at different times. And a key is every one of these models that I show here has a reforecast associated with them. So interestingly, when I ask our customers, do you know what a reforecast is? Most say no. So it turns out the maximum value is derived from an ensemble forecast when you leverage reforecast data. As an example, for the ECMWF seasonal model, it starts running on the 1st of the month. So on June 1st, they'll start running it. It'll be available on the 5th of the month, but they run a 20-year reforecast. So they take June 1st, 2024, June 1st, 2023, June 1st, 2022, and they run the model again. The reason they do that is they can update the code, they could change a parameterization, and then you have a history of model forecasts to be able to tune the skill of the model. But the point is all of these have a reforecast available. So I mentioned the ECMWF is a lot of data. The ECMWF Extended, they now do a reforecast every odd day. So the 1st, the 3rd, the 5th. And so we have to do what's called calibration on the fly. So the model data is coming in, we're recalibrating. And then as the real-time forecast information is coming in, we're applying that calibration process. Whoops, wrong way. Right, and so then the point is that you use the reforecast to improve the models, and then as the real-time forecasts become available, you're integrating that real-time data, applying the improvements, and releasing a forecast. So I want to make sure that we all understand what we're talking about. So a long-range forecast, right? So beyond initial condition predictability, you really need to talk in terms of probability. And so the traditional long-range forecast is a tercile forecast. And that means you're forecasting the probability of below normal conditions, and above normal conditions. So we could take data from the Miami International Airport AWOS, that's literally right over there somewhere. And we could take 40 years of the data for today, let's say. And if we looked at the distribution, it would look something like this. It'd be a normal distribution. And we could segment those observations into the lowest 33%, the highest 33%, and the middle 33%. And so the baseline climatology is equal probabilities of 33%. And when we do a long-range forecast, then we're processing the ensemble information to find out if there's a shift in that climatological distribution. In this case, I've manufactured a forecast that is 50% below normal. So there's 50% chance of below normal forecast for whatever forecast time period this is. And then there's a very small percentage of above normal. And this is probably, say, 30% for normal conditions. And then ideally, your forecast, if you say 50% below normal, it should occur 50% of the time. So when that happens, it's called a calibrated forecast. Oops. All right, so it turns out creating a long-range S2S forecast is quite complex. And as I mentioned, so over the years, we've been dealing with this complexity. So it involves managing diverse gridded data sets, managing diverse reforecast schedules to achieve bias correction and calibration, and then implementing those real-time forecasts as well. And so just as an example for global climate data, so any of those models that I've mentioned, you have to manage different spatial resolutions, different temporal resolutions, different update frequencies, different revision timings, different versions, and different file formats. So you have to manage all of that complexity to come up with a map that shows some colors on it, right? In a way that provides value to the end user. And then likewise, an operational real-time climate service depends on selecting the best resources available for the job you're trying to achieve, and then developing robust processes for acquisition. So a good example of the last bullet, the developing robust processes, a few years ago, as 3 or 4 years ago, NOAA implemented a time rate limitation on downloading the climate forecast system data. So you could only download, you could make a request 60 requests per second. When they implemented that, we couldn't get the data fast enough. So the CFS is, let's see, it's 4 ensemble members run out 180 days in 6-hour increments for the entire globe for all the variables, right? So it ends up being a lot of data. We couldn't get it fast enough once they implemented this rate limitation. Fortunately, we switched over to the Amazon cloud distribution, and we got it faster than we ever thought possible. But the key is identifying this robust process to be able to get the data. So as it says here, model reforecasts are essential for creating the highest value product that you can. The purpose of the model reforecast is to measure the fundamental errors, right? It turns out models aren't perfect, right? Is that a surprise to anyone? Probably not. But so we use the reforecasts to measure the climatological bias. So we get 20 years of model data. We can measure the model climatology. And then you difference that model climatology from the observed climatology. And that's a correction factor that you can apply to the real-time forecast. Likewise, you can study the spread of the ensemble. And so it happens to be a mathematical optimization process. But given 40 years of ensemble spreads, you can compare how well the model simulates forecast uncertainty. And you can correct for that. And that correction is what creates a reliable forecast. So again, a reliable forecast is that you want the observed event to happen with the frequency that the probability in the forecast suggests. And so in this case, then, you have to deal with different reforecast strategies. Again, it'd be wonderful if all the modeling centers coordinated and made it easy, but they don't. And then the reforecast data has to be aligned with the real-time forecast in terms of the initialization date as well as the lead times. And then, again, it's right, combining multiple models increases the skill of the forecast, but there's a lot of complexity to do that. And so creating a multi-model ensemble of the long-range forecast increases the complexity as well. Let's see, I just covered that. So just as an example here, I've got each one of these dots represents in a theoretical month the date of release of reforecast data from a bunch of the different models. And you'll notice that very few times, in fact, no times are they all aligned. So for example, the GEFS, there's a reforecast available, but it's only initialized on Wednesdays. So every Wednesday through a year, they ran a reforecast. And so it's helpful, but it does add complexity. The ECMWF extended, I mentioned, it's a real-time reforecast released on odd dates of every month. And so you have to align all of those and manage the differences to be able to come up with a multi-model ensemble, for example. Likewise, the point of this is that the forecasts begin at different times. And so if you are making a forecast, say, for this time section, you have to manage the fact that there's a difference in skill at different lead times to try to adjust for the change in skill so that your 5-day forecast is representative of the skill of the 5-day forecast. And then, as I say, calibrated forecasts or long-range forecasts are most valuable when they're calibrated. So that is a bias correction, correcting that fundamental error, and then producing the reliable forecast. So reliability meaning that the probability of the forecast, or sorry, reliability meaning that the observation event occurs with the frequency that the probability suggests. And so another good example of a complexity is in a warming world, right? If you want to be correct in your probability forecast for temperature, you just forecast warmer than normal, and you're going to be correct almost everywhere, other than during a La Nina event. And so we address that by correcting for temperature trends and then calculating the calibration process. And what you get is you get a look at temperature based on whatever we might call today's climate. So it's variation relative to today's baseline rather than a mean climate from, say, 30 years ago. But that's the kind of it's the kind of complexity that you have to address. And then the other part, then this one is important as well. We ended up developing our own skill statistic to be able to measure the forecast, measure the accuracy of the forecast, and we call it's the fraction correct. Meaning, if we forecast above normal 60% of the time, you want the observed event to be correct 60% of the time. I keep going the wrong way. So I'm going to come back to the capacity building slide. Right, all of the complexity I just mentioned is theoretically required to get the best possible long-range forecast to enable an early warning of, say, a flooding event, a heat wave event, or a drought event. And we've been working on it 17 years from when the product first started. And I guess Kevin on the panel mentioned keeping up technologically. So one of the things that's happening today is the models are advancing pretty rapidly. So ECMWF Extended went through 2 upgrades in the last year and a half. The AIFS was just released, right? There's lots of new developments coming. And it's in our business to manage that technological evolution, but in particular, apply the fundamentals of the science to make sure the forecasts are as good as possible. And so what I would say is, so rather than trying to build that capability internally, there's an opportunity to enable capacity around long-range forecasting by leveraging a tool such as the World Climate Service or other forecasts that have the proper calibration process included. And so I attended the event in Jamaica 2.5 years ago, and I met Evan Thompson and his subordinate Jacqueline, who runs the climate department. And a few weeks after the event, I got a text from Evan that said, "Hey, we need help with a long-range forecast. Can you help?" And I got in contact with Jacqueline, and I talked to her, and I said, "Yeah, I'll help out. I'll set you up on the World Climate Service. I'll train you on it. We'll get it going for you. When's your meeting?" And she said, "Oh, it's today at 5." And so I actually prepared a forecast. I put it in PowerPoint, and I sent it to her. And then after that, a couple of days later, we did a training. But the point is, the Jamaican Met Service used the World Climate Service for about 1.5 years, and we're going to reestablish the use. And Evan, will kindly agree to at least say a few words about his use of the World Climate Service.
Thanks, Jan. Yes, we did meet some time ago. I thought it was less than 1.5 years, but maybe it was about that time. And yes, and we realized that a decade or 2 ago in Jamaica, we wouldn't have thought that we'd have needed even seasonal forecast because we kind of know what will happen. I mean, in May we get a lot of rain, and then by June, July it comes down a bit. Low period in July, and then there are some patterns that we really got so used to, and this is something that we would predict without without having the use of many of these tools. But then in recent times, we realized that all of this has changed and the seasons have changed. And when we're getting the rain is much different from when we used to. The amounts we would get would be less or more in some cases. And so we felt that we needed some help. We got quite a bit of help with seasonal forecasting, and that is done with the help of the CIMH in Barbados. And so we developed our capacity to do some amount of that using some of the tools that were available. But then we realized that, and there were greater demands on us now to be a lot more precise with our predictions and getting a little bit more scientific with, the shorter term of our seasonal forecast. So we went down to subseasonal, which we didn't have much capacity to do. So that's when we had to reach out to Jan, and there was quite a bit of assistance. The ministers, in government start to get a little bit anxious. What should we expect? I mean, the water levels are dropping so much, and we need to be trucking water to certain areas because of the drought situations, that kind of thing. So we needed to find a way to to move into this new dimension where we were able to move into the sub-seasonal forecasting, and Jan came to our rescue. And we found that the World Climate Service has been very useful, what we have been getting in terms of the products, and of course the capacity to be able to, at least now look at how what we should expect in a shorter period of time with sub-seasonal forecasting has really been useful. We're planning to get a little bit deeper in our engagement with Jan and with Prescient Weather and World Climate Service, and just making sure that we do have the capacity to do what we need to do, because the demands are growing, our seasons are changing, and of course, with not only climate change, but also with just the variability of climate, there is the need for that support. So we thank you very much.
So I will end by saying, by going the wrong way again, I will end by saying, if you're curious, we are happy to set up a trial, right? So I started off by saying, we think we can, we're all here because we think we can solve a technological problem. But to highlight the conversation that just happened, we're here because we think we can help. And honestly, I would love to help with this particular problem. It's a difficult problem, and I believe we have a good solution that can help out. Thanks a lot.